Hello viewers, you're welcome back to the second edition of this video on hydroelectric power plant modeling with Simscape, which is a MATLAB Simulink add-in that allows you to model physical systems such as fluid, hydraulic, rotation, shaft, electromagnetic, mechatronic system, mechanical system. A lot of complex systems can be modeled with Simulink using libraries that are very useful and sophisticated for modeling dynamics of physical system. So, I was working on creating an hydroelectric power plant model with Simulink, and we have connected the blocks that we are going to be using. Our next task is specifying the parameters for the blocks in order to model the system. So in doing that, I have this. If you open my current folder, I have this MATLAB scripts that I've written for running the parameters. So this is the script I want to be using for running the parameters. So we have some values that I specify for some variable that will be generated and will be used in the script. So you have the height, the diameter, hydraulic diameter for the pipe. This is the gravitational constant. This is the height of reservoir, water reservoir. This is the inertia for the wheel. Then the K generation, the J ratio, the T nominal. This will be the damping factor for the damper in the wheel rotational movement. Then the pipe length will be given here. Then the load, resistance, then the density of water is also given. Then the volumetric displacement that the wheel is going to be written will be given from here. So I'll be putting all these parameters in the model in order to fully solve the model. So whenever I want to change the values, I can easily change it with MATLAB. Then I can write some code that will work with the system to solve more complex scenario for the model. So in order to save this in the database, I will be running the scripts so that we have it in the workspace for the MATLAB. So I think it's in the workspace already. So you can see them in the workspace of MATLAB. So then I'll be going to the simulation to specify them in the blocks. So the first thing is, okay, there is something that I need to add here. The property of the stream. I think I forgot in the previous video that I did. So I'm going to add like another block to specify the property of the stream. So that block is we used to call it I don't know where can we have it. I have to look for it. Element. It's supposed to be in under element. Okay, utilities. So you have it in the utility setting. So these blocks help in setting the property of the fluid, such as you might want to set the density, the viscosity, the fluid dynamics property that will affect the way the fluid will respond in dynamic system. So this section of the model is basically a fluid system. So you want to set like the chemical intensity property of the system, like the way the density is going to be. You can use this block to do that. So you just connect the block to the line, then you can set the properties. So for example, you have the density atmospheric pressure, so you can put the density data here. Then you have the other property here. So I think for the density I have a variable for that rho. So I'm going to be writing rho there, so it will specify the density. So I have rho. So you can see, you can easily pick it there. So you have the isothermal bulk modulus, the kinematic viscosity, So if you want to change it, you can change it. There is basically all these properties are basically that of water. So then you have the atmospheric pressure, and if it is there have some air there, you can specify all those air properties here. So it's basically used to model liquid in isothermal condition. So then you have this for the pressure source in the line. So the pressure source is going to be using the Bernoulli principle, which is the density rho g dh. You understand? So I'm going to be writing rho times g times height of reservoir. So you can easily be searching them and be writing them. So you are going to have it. So the unit is going to be in SI unit, Pascal. So I think this one is also in SI units, kilogram per meter square. So it's not going to be wrong. Then you have the pipe. So for the pipe length variable is given. Okay. Pipe length variable is available. Then the cross-sectional area is pi r square. So you can easily use MATLAB function pi. Then you multiply with the radius, which is the hydraulic diameter divided by 2, dh divided by 2 divided by 2 all square. Where is this? Pi d square, or you can say pi d square over 2. Just say d raised to power 2. Let's write it like this: over 2 divided by 4. Pi d raised to power 2 divided by 4. So then this one will be dh. So I'll be copying this because I will need it to the other time. So if you want to model any friction loss, you can adjust all these values. You understand? So let's just leave it at the initial condition. So I'm going to do that for this other side. This will be pipe length, the function for the area calculation, then the hydraulic diameter dh for this. You have to be sure of the case so that you don't make any mistake. So then for this, I'm going to have the I to be variable. The restriction area should be variable, so it's going to be controlled by this AR signal. So the minimum area is 1 e raised to power minus 10 meter cube. The maximum is 0.005. You understand? So it's going to be varying the area based on this value. So let's increase this one to 1 or so, 1 meter cube, so that let's start, because that area is too small to mark. 0.005 is too small. So let's start with 1. Then you have the discharge coefficient 0.64 is the factor of volumetric flow and the area. You understand? So it's like a constant. So compile time. Then you have the critical readings number for the flow in the line, so that it is realistic, or giving you a realistic result. Then we have this. In this, you have the velocity displacement 0.64. Then the critical readings 0.15. Okay. So for this is the settings: mechanical rotation, pressure at point A relative to, so it is showing you so that you know where to have the rotation. Then the angular rotation based on the normal direction. So you can also interchange it, but don't just make mistake. So the initial rotation is 0 rad. Then the initial volumetric flow rate displacement is given. Then the interface volumetric displacement, so we write it to be volume displacement that we give. You understand? Then the environmental pressure, atmospheric pressure, specified pressure, you understand, for the environment, like the ending point where the flow will be going to, you understand, where the flow rate will be, like the pressure of the reservoir for the well, you understand, at the end point of the well. So then you have this damping factor. So we specify damping factor, which is B in this place in Newton meter per seconds. So make sure it's in the standard units. So that then this inertia I will in standard unit. So then this one is the ratio. So we write R gear. So this is the gear ratio. So the value is also given. Then I think all these sensors, you don't need any settings for them. You just, if you want to add acceleration, you add it. Wrap angle, you also put it 0 and 2 pi. So for this setting, you use the kgen for the generator that we have specified. All this you can just put numerical value there. It will still work if you put a numerical value there. So then I'm coming. Okay. For the resistance, you put the load, R load for the resistance. So I think I've done that. So all these are just sensors. They sense the voltage, the current, and send it to the signal. I think they have two outlets here, so you don't need to worry. Then you get your power for the sensor. So I can save the simulation. I think, okay, let me do something. In order to control the ratio, I want to design a controller that is going to be adjusting the valve opening and using it to control the rotation of the generator, so that it is not too high and it's going to maintain the power that we want. You can be sensing the power, you can be sensing the voltage, anyone that you want to be sensing, you understand, to design a controller for the system. So that's one of the power of this system. So I'm going to pick I'm going to design a discretized PID controller for the system. So I'm going to go here, add. Okay, let's add a subtract block. Okay, I think the way I added a subtract block, let me just open the library and go to this place, discrete PID controller. I need a unit delay because I want to use a discrete controller. Then I need a subtract. Okay, let me use a sum. Can I use both of them? Can use a subtract, can use a sum. Then I'll have a source, a constant. I have a constant here to set my speed. This will be going from here to this place. Valve opening. So this place is going to the subtractor. Okay. You can even do this like this, flip it like this. Now rotate this, flip it. Okay. Rotate this, flip it. Okay. So this is really constant. So I will set the angular speed from here. This will be connected to this place. This is sent, the error is sent to the controller, and the velocity is what I want to be measuring. I want to be controlling the velocity. So I'll set the sampling time, which I'm controlling the velocity, angular velocity. I don't want it to be too high. This is the valve opening that I'm using, and it's going to be sending the signal to this controller. So it's going to be subtracting the velocity from where I get it, then sending the error to the controller to adjust the system. Coming. Want to see if there is any problem. Let me rotate this. Okay. So you have this is add and subtract and the like. So then I'm coming. So the meaning of having -1 is it's going to inherit the sampling time from the control, from the connecting line, maybe from this, you understand. That's how it's going to be using to sample it. So it's going to be inheriting from this controller. So then you have this addition and subtraction blocks. You can change it to be round if you want it to be round. You can apply it, so it's going to be oval shape. So let me change it to the box. I think I like the box better. So the controller will be opened. So you can see this is a PI controller. The validity time is 0. So I can change it to a PI controller. So the source is integration. So I'm calling this one 1E. Let me make it to be slow, 1E minus 6. It's small thing, and let's say 1E5. 5E minus 3 for the integration time. So you can tune the controller to fully see the response of the system with time, how it's going to be changing with time and the likes. Then this control set point will be set to 500. So it's going to be a set point. So I think that's everything for the valve opening. You can see the response, the displacement and the likes, and then I can even check the signal in the scope. So I will be checking the signal with the scope too, to see the valve opening signal, how it is changing with time. You understand? So from there you have the current, the voltage and the likes. So let's run it for 10 seconds or so. Let's run it for 10 seconds and see the influence on the system. So I don't think there is any problem. I just run it for 10 seconds. So it's compiling. Okay, it's done. So you can see the results from the scope. Okay, so this is the result of the controller 500. And see the results 500, and this is very small. I can barely even see the data. Okay, this is now the power from the results. This is the power profile that is generated from the system. Okay, you can on this to see the legend. You can on this, show legends to see the legend. So this is the voltage, the blue is the power, and this is the current flowing through the line. So um, can ask for the density of the line, 500 sampling time. I think I need to work on the sampling time of this controller. Let's put it 0.05. And that's why. Let's run it with this sampling time and see. Okay, then we have a smoother curve now with less error. I think this is better. Then if you see the power curve, this is better. You can see the voltage and the current with time. This is better. So let me delay this for, let me delay this one to 0.1. Let's see if I delay this to 0.1. Let's see the influence on the results. So if I delete the other one, it doesn't really have effect. Okay, that is an overshoot. That's it. Just from the delay, that's an overshoot. So we can set it to be 0.05, the same as the other one. See, there's an overshoot in the dynamic. And you have it like this. So that's the speed. For that kind, for 500 speed, the power that you should be expecting should be 100 watts 100 watts of energy. Then we can do something, decrease the height by half. Let me multiply it by times 0.5 and see the influence on the system when we decrease the height by half. And we decrease the height by half, we are able to control the speed. Then the power, let's say the power, we are able to get the same power out of it. You understand? But the orifice you have to open more. You understand? The orifice we have to open more. I think you can separate them by doing something. What's this thing that they used to do? Okay, I have to use 3. You can see the valve opening is now 0.7 or so. So I'm going to do that for the other one too. After here. So you can see the current, the power, and the other one. So change the parameters by increasing the height, the diameter. I'm talking about, this is diameter. Okay, decreasing the height 0.5. I even decrease the diameter, not the height. Leave all this heat. Okay, leave the diameter, just decrease the height. All these are fixed parameters. Then increase the load. So let's see the reference, the results. So I still need to do something. I still need to run it to update the code. I think that's why I have not even seen any reference on this. You have to run it to update the code. So let's see the result. based on this data. So I see it doesn't really reach 500. Doesn't really reach 500 based on the new reference point, and the pi is somehow it doesn't reach 100. Yes, so I can change the, let's just say 0.6, 0.8 of the reference side. So that's what you are going to know, which one that you can change in the model to get your perfect design for your hydroelectric power plant, where to put the dam for the optimum design for the hydroelectric power plant. So we are able to get your set point. The angular displacement is increasing. Then you have the variable plane, you can see 0.9. When it reaches 1, that's the ending point. It can't increase further. You understand? So then if you close this, you see the power, you are able to get your 100 watts. You can see the current and the voltage, the way they are changing. You understand? So I think with this video I'm able to explain the simulation of hydroelectric power plant. Much can still be done on the process. When you are able to create the model, you can do a lot of analysis on it. So if you have any work concerning this, you can meet together and discuss it together, and you can work on a lot of designing projects. This was the credit, the onset of everything. If we have created this, there's a lot of research that can be done on it, a lot of controller design that can be done with these two that we have to design a small scale electrical system, grid system, grid integration using a powerful Simscape software. So I will really love to hear more about it from you guys. A lot of text on ideas on this thing. So thank you for your time. I really appreciate. So stay tuned to our channel and suggest more videos that we can do that you need us to shed light on. So I am your host. I remain your host, Abdurrahim Babatunde Kukwala. Thank you very much.